right, hopefully you all can see this, and I clicked too quickly. I want to put my laser pointer. All right. Hi, so I am David Rodriguez, and I'm going to be talking about AstrodbKit2. And yeah, I'm just going to go ahead and go to the next screen so you can see a little bit of my contact information. I am an astronomical data scientist at the Space Telescope Science Institute in Baltimore, Maryland, USA. We're always hiring, so go to this page if you want to see more details of that. The particular project, however, I'm going to talk about is something I did in collaboration with BDNYC. This is the Brown Dwarf Research Group in New York City. And you may ask, what's a brown dwarf? Thank you for asking. So a brown dwarf is an astrophysical object, is an astronomical object that is sort of between a star and a planet in terms of some of its properties. So to tie it back to this morning's keynote about nuclear fusion, a brown dwarf is generally not big enough to sustain nuclear fusion throughout its entire lifetime, unlike a star like our sun. So it's a very interesting object to explore. And our research team was sort of looking at this collection of brown dwarf and wanted to have a database that they could have to share properties and discuss, future science goals and things like that. So AstrodbKit2 is a database management tool that we've created and prototyped with the brown dwarf sort of research community in mind. However, it does apply in general to other astrophysical objects and, of course, in general as well to other things. A couple of key use cases that we have to keep in mind. We want to build something that is collaborative, a collaborative design for the database, in particular to the data as the sort of top goal. We want to be able to access the data locally on individual machines, have thousands of sources, and represent complex data in simple fashion. I'll put on my sort of product owner hat and say, hey, it's very important to be upfront and clear about your use cases whenever you have a project. Notice here, for example, that performance and scaling, that is not a use case. So I will caution you that if you are trying to do exactly this for millions of sources or billions of sources, big data, you will probably run into some issues that we just were not worried about because our design was, we have thousands of objects, we want to explore them sort of deep down in detail. So not big data, smart data is one way you could think about this. So at its core, this is going to build a relational database or something you can use with SQL, but it's going to have a JSON document store on the backend to facilitate the collaborative aspects of this. So how do you get started with this, right? So you would code up your database with something like SQLAlchemy. This tool is built on top of SQLAlchemy. So you would define your various tables as classes with your various columns, foreign keys, etc., that you might want to do. And you would import that. So this simple.schema, this is this schema.py file. It's basically the description of what my database would look like. I have a connection string. In this case, I'm using SQLite and just creating a binary file and creating an empty database with this schema. I can then connect to this database. Now, if the database had contents, I don't have to do anything else. But if it doesn't, I can do .load database to load an entire directory worth of data into my database. And I can do anything else, right? I can do modifications, I can do queries, plots, etc. And if I do modify anything, I can save it then back to that database directory. I will point out there are some subtleties here I'm glossing over in the interest of time. So do check out our documentation for help if you do are intending to use this. When you save the database, you're going to create a bunch of JSON files. Again, one of the reasons why this is sort of optimized for thousands of objects, not millions. And this is what they look like, right? You have a variety of keys that are essentially the various tables in your database, and they're all pointing back to a primary source table that describes the basic properties of your objects. And so this one brown dwarf and all of the metadata that we want to capture for it. And because this is a text file, you have the ability to use something like Git version control. And so you can see on the left is all the sort of Git blame history. For this object, you can see that 8 months ago, I added a new table information spectral types for this particular object. So this object will grow and will have a history of how metadata and data is being added to this particular, the properties of this particular thing. And so the goal of this is that we facilitate this particular workflow. you have on your end, you have a local database copy, you're implementing changes, you're generating your JSON files, you're pushing them to GitHub. And on GitHub, you're reviewing the changes with the rest of the team. There's also automation there to verify that the data work, that there's no validation issues, integrity errors, that sort of thing. And when we have a pull request that is merged, we can also trigger automation to produce a sort of production level ready version of that database that we can send to a web application. So there's an example web application. If you go to simple BB for Brown Dwarf, archive.org, this is a Flask application that's basically running a database powered by this workflow. So this should look very similar because it's standard software development workflow, except instead of managing software, we're managing the database content. And with that, I think I am done with my